Okay, question on the last two in 2.5, is that correct? So we talked a little about these last week. And the key here is to convert, they want your answer in feet degrees. Anytime you find the derivative of sine or cosine and you plug in an angle, your answer will always be in radians. Because differentiating sine or cosine only works when you're in radians. It won't work when you're in degrees. So your answer will always output a unit of measurement over degrees. Or sorry, a unit of measurement over radians. But a lot of times we don't think in radians, we think in degrees. So we want to know how fast this x is changing with respect to theta when theta is 45 degrees and when it changes 1 degree. Right? So I want to know how fast is the ladder sliding down at that point. So going through, this is 2.5. So let's look through the setup here. I have theta, 6, and x. So this is number 31 on 2.5. I know, it's a little different, but no one's going to have a seizure for seeing the different colors. Okay, so eventually in Chapter 3 we'll get into related rates of change, which are word problems. They'll say, find the rate of change of the radius with respect to the surface area, or various different relationships. Here they're wanting you to write your own equation, differentiate that equation, and then plug in your points. So I think x was given to be, come back here, what was x given to be? Oh, okay, no, theta was given to be 45. So the relationship would be sine of theta equals x over 6, right? So I could write that as 6 sine of theta equals x. Now if I differentiate this with respect to with respect to t, so I'm differentiating this with respect to t. Theta is changing and x is changing with respect to time, right? If I let this ladder slide down this brick wall and I can freeze time and I play time, theta is moving and x is moving. The only thing that's not changing is the 6, the length of the ladder. So now what's the derivative of 6 sine of theta?
6 cosine theta.
Good. What's the derivative of x?
1.
With respect to t? This is what you're wanting to find. Right? The derivative of x with respect to t is how fast is x changing with respect to time. That's dx dt. So now I want to plug in theta to be 45. So I would have 6 times square root of 2 over 2 equals dx dt. Right? So I have 3 square root of 2. But that would be my answer in radians, feet radians or meters radians. So I'd have 3 square root of 2 meters radians. And I want meters degrees. So do you guys remember how to convert radian measured to degrees measured? Question?
I had a question. You get the square root of 2 over 2 because it gives you the angle 45 degrees, right?
Yes.
Okay.
So cosine of 45 is 1 over square root of 2, and if I rationalize that, square root of 2 over 2, so I get 3 square root of 2. Okay, so now if I want to take 3 square root of 2 times pi over 180, what does that give me? We did this in the last class. It was 0.07. Meters degrees.
Would you have to convert it to feet? Meters?
Was it in feet or was it in meters? One of the examples was in feet and one was in meters. So I think I might have remembered them incorrectly. So this example was in feet. This example is in meters. So here everything would be feet. Right? The next example, everything's in meters. Everything's given in meters, so there's nothing to convert there. And then you use tangent, and you go through and do the same thing, plug in 45 degrees, and then once you get your answer for that, it will want it in degrees, so you need to multiply by pi, divide by 180, right? This is converting from radians to degrees. If you want to go from degrees to radians, you multiply by 180 and divide by pi. Any questions on that? Any other questions on the Wiley homework due tonight? Question?
2.6.
2.6? One, two, three, four, five. This one?
Yeah.
So when I did these, I did some of these in class. I don't know if you were here on Thursday or Wednesday last week. I wanted to show the different ways to input that. So multiple different ways you can input that. You can multiply 8 out front, x cubed, various different things. Do you have like a concept question or what's going wrong? So you take the derivative of the first function. So the derivative of x cubed would be 3x squared. Hold the second function, which is sine of 4x squared. Some students were having some issues entering that. So if I want to enter sine, if I put in sine, it automatically puts, say if I put 2x. And then they don't know how to square it. So if you highlight everything with sine and hit shift 6, it will give you the proper square. Another way you can do it is just get the form to begin with, meaning something squared, and then whatever you put in here, sine of 2x, and that will also give you the square. But if you just highlight the 2x and hit the shift, the square will be on the wrong part of it. You're squaring the 2x, not the sine of 2x. So sometimes, I think some students had some entering issues. But then the next one, I hold the second function, I take the derivative of the first function, which would be 2 sine of 4x to the first power, but you don't write the first power. The derivative of sine would be cosine evaluated at 4x times 4. Can you see that? Maybe you can watch that video that we had from Wednesday class, because we did some of these on Wednesday. Any other questions on 2.6?
The last one with the graph?
The last one with the graph. This is a good question, and let's look at this one. So this is 2.6. This is number 67. You're given this graph that says -2, -4, 2, oops, 0, 2. This would be 10, 8. Okay. So your function is the derivative with respect to x of the square root of x plus the value of the function at x, and you want to evaluate that at x equals 2. -2, sorry. This example, you're doing it at -2. Okay, so now I need to differentiate this function and then plug in -2. So what's the derivative of the outside?
1/2.
Mm-hmm. Right? Derivative of the outside evaluated the inside times the derivative of the inside, which would be 1 plus f prime of x. So now if I evaluate it at -2, I have 1/2 -2 plus f of -2. What is the value of the function at -2? 8. to the minus 1/2 power times 1 plus, what is the derivative at minus 2? What's the slope?
2.
Be careful because it's going up 2 and over 2. So what would it be? 1.
So I can skip over.
What?
This, and just like move it.
Yeah, sorry. So let's go back to the picture real quick. So you can see I go up 2 over 2, right? So the slope looks like it has a positive slope of 1, but it's actually 2 over 2, which is 1, sorry. 2 over 2.
I missed the x-axis change.
Yeah, you have to be careful with that. So you go up 2 and over 2, so the slope is 1. But if your x-axis was 1, the slope would be 2. Does everyone see that? Does everyone kind of see the form? That I don't know what this function's called, but I can just take the derivative of the function, and when I plug in minus 2, I get a positive 1. So then evaluating this, this would be 2, which would be canceled here, 6. So I have 6 to the minus 1/2. So I have 1 over square root of 6. Does it want you to put it in as an exact answer? So 1 divided by square root of 6. It should accept that. If not, they might want you to rationalize it, square root of 6 over 6, but this should accept it. Is it positive? Yes.
How did you know to put 8 in for that f of x and then?
So what this is saying is the value of the function at minus 2. This is saying the slope at minus 2. This is the value at x equals minus 2, and this is the slope at x equals minus 2. So if I look at the picture, it gives me the value at minus 2 is a positive 8. And the slope is 2 over 2, because it's linear here, and the slope would be 1. So this would be 1 over square root of 6. I don't like that. It's perfectly fine. Any other questions on 2.6? Any other questions on anything due tonight? Yes?
On that last one on 2.5, the
Tangent?
yeah, when you find the derivative of that, you'll have to.
You have secant squared, right? The derivative of tangent,
Okay.
secant squared.
Okay.
If it was like cotangent, then you would have cosecant, cotangent, right?
Yeah.
No, you would have cosecant squared. If you had cosecant, it'd be cosecant, cotangent. So
Then how would you do that?
you would just plug it in to the two different
to
points.
2 of them
Yeah.
and then multiply them?
Then multiply them.
Okay.
But here you would have the derivative of tangent secant squared, so when you plug in 45 degrees, you have 1 over square root of 2. So then 1 over, no, sorry, you have square root of 2. It would just be square root of 2. Square root of 2 squared is 2. Make sense? Sorry, I know it's just a lot of words, but I think you can follow it. Anyone have any other questions?
I just have one question just to make sure that our quiz is on Wednesday this week.
On Wednesday this week.
Or on the schedules this way.
I don't have the schedule in front of me because I give that away. Yeah, so. Okay, so I really don't know what's going to happen tomorrow. If we'll even be here, so let's potentially push the quiz back to Thursday or Monday, depending on what happens this week. So there won't be a quiz on Wednesday, for sure. But I will still give you that quiz for the opportunity to take your best 8 quizzes. So it might be another Wiley quiz. We'll just kind of see how it goes. Question?
When do we have a due date for the next homework? I don't know if you said that already.
Yeah, I said it.
The 8th more?
Yeah, it's like the Friday before the test.
Okay.
So I haven't written any of that up exact. I'll send you guys an email out with that information when I'm going to collect it and what's it going to cover. And then I'll know what the next test is going to cover so you can start preparing for that. Any other questions? Okay, so that was the that was some questions from the homework. So let's talk about the next section, which would be the beginning of chapter 3, 3.1. So 3.1. is implicit differentiation. Implicit differentiation becomes really handy when you can't write y as a function of x. Because in the real world, writing y as this nice, pretty function is relatively hard to do. So we can still talk about the slope of the function at any point, being able to use implicit differentiation. So not all functions can be written in the form y equals f of x. So an equation of the form y equals f of x is said to define y explicitly. And notice I didn't say function, I said equation. Because not all equations are functions. But when an equation passes the vertical line test, it becomes a function, right? So we'll talk a little bit about being able to solve for y explicitly. So if you think of like x squared plus y squared equals 1, that's a circle centered at 0, 0. That's not an equation. Sorry, that's not a function, it's an equation. It represents the set of points that are a distance of 1 from the origin, right? So that's an equation, but for it to be a function, it needs to define y explicitly. So if I look at the example, x squared plus y squared equals 1, this is an equation. It's not a function, right? It's not a function because it doesn't pass the vertical line test. If I was to graph this, I would get a circle centered at 0, 0 with radius 1. If I solve for y, then this top part would be y equals the square root of 1 minus x squared, right? This bottom part would be y equals minus the square root of 1 minus x squared. Okay. These are two functions that represent these equations, right? If I graph y equals 1 minus the square root of x and y equals minus the square root of 1 minus x, I would get a circle centered at 0, 0 with radius 1. But this is not a function. You guys see that? But this is an explicit representation of this function. This relationship is called an implicit relationship. It's an implicit form. So equation can implicitly define more than one function. So don't get too caught up on explicit, implicit, equation, and function. It's some terminology that comes up, but hopefully I don't think it will stump anyone on the actual calculus of it. So let's look at implicit differentiation. So sometimes it's possible to solve for y and then find the derivative here. But remember what the derivative means. The derivative means the slope at any point, right? And a lot of times you're only given an x value. If I said x is a half, what is y? Y has two outputs, which we automatically know that's a problem when we're talking about functions. So in this chapter, or in 3.1 specifically, it will give you find the slope at x equals 10, y equals 3. So it will tell you the point 10, 3, or 10 minus 3. So you see here that this point is going to be this point is going to be related to this function, and this point down here is going to be related to this function. And I can differentiate this function, right? It's a chain rule. Derivative of the outside evaluated the inside times the derivative of the inside. The same thing here, but here the derivative is going to end up being positive because the derivative of the inside is minus 2x, cancels with this negative. And the derivative here is going to be negative, which makes sense, right? The slope is negative here and positive here. Do you guys see that? I mean, this is all kind of going through this whole process. However, I can use implicit differentiation, differentiate the top function with dy dx, and then plug in my x value and my y value to get the possible slope. My x value is positive here, my y value is positive. Here my x value is positive, but my y value is negative. So that's all going to come into play. So let's look at implicit differentiation. So implicit differentiation. So it's not necessary in general to solve an equation for y in terms of x in order to differentiate. Okay, so we're going to look at an example where we do implicit differentiation and then the original differentiation, and we should get the same answer. So let's look at a relatively simple relationship. X times y equals 1. I can solve for y, right? So if I solve for y, I get y equals 1 over x. What is the derivative of 1 over x?
Minus x to the power minus 2.
Good. So doing implicit differentiation, I should get the same thing. So implicit differentiation, I'm going to differentiate this relationship with respect to x. So that tells me the derivative of x is going to be with respect to x. The derivative of y is what we want to find, the derivative of y with respect to x. So this term, x times y, that's a product rule. The derivative of the first function, hold the second one, plus the derivative of the second function, hold the first one. X is a function of x. I mean, x is x, right? Y is a function of x. So what's the derivative of x with respect to x? 1. What's the derivative of y with respect to x? dy over dx. It's the derivative of y with respect to x. I don't know what that is. That's what I'm trying to find. So we call that dy dx. So if I say the derivative of the first function, hold the second one. So I have 1 times y plus x times dy dx equals, what's the derivative of 1? 0. So now I have this relationship and I want to solve for dy dx. dy dx is what I want to find. So does anyone have any questions how I got this?
Yeah, what did you do?
So I took the derivative of x, held y. I got that. Does anyone have any questions on that? This step, I held x and I took the derivative of y. The derivative of y is what we're looking for, dy dx. that make sense? Eventually, we'll type the derivative with respect to t or something. So if x is a function of t and y is a function of t, then I'm going to have to do that separately. And that's really Calc 3. You'll get into multiple variable calculus. Here in implicit differentiation, we have two variables, an x and y, but y is really a function of x. So anytime we differentiate it, we have to treat it as dy dx, right? So now if I solve for dy dx, so what do I get? I get dy over dx equals minus y over x. Does anyone have any questions on how I did that? It's algebra, right? I took the minus y, I took minus y over here, divided by x, and I got dy dx. So does this look like this? Not exactly, right? This is y over x, and this is minus x to minus 2. But could I write y as a function of x? Sure I can. I did it right here, right? So let's plug what y is in terms of only x and see if that the derivative equals the same thing we did the original way. So if I plug minus 1 over x, that gives me minus 1 over x squared, which gives me minus x to minus 2. Now does it look the same? Yes. So here this is the derivative as a function of x and y. If y can be written as a function of only x, you can write it like this, which would be the original thing what we got here, right? However, sometimes it's impossible to solve for y by itself. And when it's impossible to do that, you can leave your answer as a term of x and y. Does anyone have any questions how I show that they're really the same thing?
Where do you get a function of y?
How did I solve for y?
Like the function, like
This is saying that the slope at any point is going to be the relationship you take minus the y value over the x value. So let's look at some points. So what are some points? This would be if x was 1, y would be 1. If x was 2, y would be a half. If x was a half, y would be 2, right? Those are 3 separate points that satisfy the relationship. X times y equals 1. 1 times 1 is 1. A half times 2 is 1. 2 times a half is 1. So the slope, dy over dx, would be minus y over x. So if x was 1 and y was 1, you'd have minus 1, right? Here the slope, dy over dx, equals minus x to the minus 2. So if x was 1, you get minus 1. You see how you're going to get the same thing? In this column, you only need the x value. But if you're going to do this way, you need an x value and a y value. Make sense? You can get the same. Now that you have the slope, you can find the equation of the tangent line depending on your point in the slope. Question?
So whenever you substitute the negative y, you just take that original equation and it was, you divide the x, so it's 1, or y equals 1 over x, and then negative.
Well, the negative was there, right?
Yeah.
So I had 1 over x
So you use
divided by x.
Oh, right.
Huh?
You use the original.
I used the original equation and solved for y. So this is what y equals in terms of x. I plugged that in here, and I got that the derivative only in terms of x. Anytime you can limit your variables, that's going to make your life a little easier. I only had to plug in 1 variable instead of 2. But however, you're not going to be able to do that in many cases. So implicit differentiation is powerful, the fact that if you know your x value and your y value, then you can find the slope at any point by doing implicit differentiation. So let's look at another example where that comes up. So this is number 6 from your book. We have x cubed y squared minus 5x squared y plus x equals 1. and I want to find dy dx. That's what I'm looking for. So I had to do the product rule, and then straightforward. So let's look at this term. What's the derivative of the first function? 3x squared, hold the second function, plus, what's the derivative of the second function? 2y times dy dx. So it's kind of a chain rule. Why is this thing we don't know? We want to find the derivative of y with respect to x. So I take the derivative of the outside, evaluated at the inside, times the derivative of the inside. The derivative of y is dy dx, right? So I have 2y times dy dx times x cubed. So that is the derivative of the first term. Everyone understand where 3x squared comes from? And then the y squared because I held it? Plus, does everyone understand the x cubed comes from because I held it? This is really the only thing new we're doing. And that's the derivative. Anytime I'm dealing with y, I have to remind myself it's dy dx. So the derivative of y squared is 2y times dy dx. What would be the derivative of y cubed? Very good. 3y squared times dy dx. Right? The derivative of the outside evaluated the inside times the derivative of the inside. The derivative of the inside here is dy dx. You could think of the same thing. What's the derivative of x? Right? Because you're taking it with respect to x. So you can think of the chain rule here, the derivative of the outside evaluated the inside times the derivative of the inside, but the derivative of x with respect to x is 1. The derivative of y with respect to x is dy dx, and that's what you're looking for. If you miss that part, you won't have a dy dx to solve for in your equation. All right, question?
So technically you'd be writing it'd be like dx over dx next to the x's? So
You could think of it that way.
That would be the one that you're talking about?
Yes. Yeah. So yeah, if you would say dx over dx, that's 1.
Okay.
The derivative of x with respect to x is 1. The derivative of y with respect to x is what you're looking for. This is what you're looking for. So you need to put that in there. All right? So does anyone have any questions on those first two terms?
So we haven't even gotten to the minus 5x.
Not yet.
Okay,
So
so-
only this is the derivative here.
So this is the derivative, so I get the first part and then the derivative of the y squared,
Mm-hmm.
but y is it the chain rule right there?
It is the chain rule. The derivative of the outside evaluated at the inside times the derivative of the inside. The derivative of y is dy dx. So y squared would be 2y to the first power times dy dx. So let's look at the second term. Oh, this pen is dying. Okay, so what is the derivative of minus 5x squared y?
Minus 10xy.
Very good. So I have minus 10xy.
Then dy plus dy.
So I took the derivative of the first, held the second one, plus, but it's going to be minus, right? Minus 5x squared. That's the first function. What's the derivative of y? Dy dx. So the dy dx goes here. So these two terms come from the second term.
Sorry, I don't get it.
So you understand the 10xy?
Yeah.
So now if I take the derivative of x squared, I get 10x minus 10x,
Yeah.
hold the y, plus the derivative of y, hold the 5x squared. So I hold 5x squared and I take the derivative of y. The derivative of y would be dy dx.
So why did you have minus? Because you distribute the negative?
Because I held the minus 5x squared. You can think of it as distributing the negative, yeah. I could have put plus a minus, but. Any questions on that? plus, what's the derivative of x with respect to x? 1? So this is 3. 1, 2, 3, 4. What's the derivative of 1? 0. So now I've simplified this to an algebraic expression, and I want to solve for dy dx. So I need to get dy dx on one side, everything else on the other side, divide by, factor out a dy dx, and simplify. So I have 2x cubed y dy dx minus 5x squared dy dx equals minus 3x squared y plus 10xy minus 1.
The y squared, 3x squared, y squared.
Yes, thank you. Minus 3x squared y squared. Does everyone see that? So I left this here, and I left this on the left-hand side of the equal sign. Equals, I moved this over, so I subtract it. Moved this over, so I added it, and moved this over, so I subtract it. So now I have terms that have the dy dx in them on the left-hand side and terms that don't on the right-hand side. So now I need to factor out a dy dx. 2x cubed y minus 5x squared equals minus 3x squared y squared plus 10xy minus 1. Divide both sides by 2x cubed y minus 5x squared, and it gives me my answer for dy dx. Minus 3x squared y squared plus 10xy minus 1 over 2x cubed y minus 5x squared. So you see that the slope is a function of x and y. So if I wanted to evaluate the slope at a point, I would need an x point and a y point.
And we don't have a way to just evaluate it, to make it to where you can just evaluate it at an x point, right?
In this specific instance, this is actually an equation of a quadratic in y. So I could use the quadratic formula to solve for y in terms of x explicitly. I might have two functions. I will end up having two functions, and it's going to be messy. It's possible. You won't be asked to do that, though, if it's ridiculous. If it's something like 1 over x, sure, you might be asked to do that. But in this case, no. Any questions on this? So the point would have to make sense for the relationship. Like x could never be 0, right? Because the left-hand side and the right-hand side wouldn't equal each other if x was 0. So the point needs to make sense. And the point generally does make sense. If they ask you to evaluate it at a certain point, it will make sense to the equation. Okay, so let's look at one that has an extra level in it. But conceptually, it's the same information. So this is number 10. So find dy dx for the equation cosine of x times y squared equals y. The only way to do this one is by implicit differentiation. So implicit differentiation says I'm going to differentiate the whole equation in terms of x. So what is going to be the derivative of cosine of x times y squared? Right? Derivative of the outside, evaluate it at the inside. You don't change the inside. Times the derivative of the inside. And this is where parentheses are very important. So what's the derivative of the inside?
Y is 2y divided.
Okay, so I heard y squared plus 2y dy dx. What am I missing? Dx, right? So the derivative of the outside evaluated the inside times the derivative of the inside, right? So the derivative of x is 1. So I have 1 times dy dx plus the derivative of y squared, which is 2y dy dx times x.
You hold both of them after you take both of them.
So yeah, so this is a chain rule problem. So you take the derivative of the outside, evaluate the inside, times the derivative of the inside. The derivative of the inside is what's in bracket. Right?
Where'd the plus come from?
This plus the product rule, the derivative
This is times, okay.
the product rule, yeah. So the derivative of the first one, hold the second one, plus the derivative of the second one, hold the first one. And that's exactly what we did, right? So now I'm
Is it y squared though, not
well, the derivative of x is 1, so hold the second function. So that would be holding x.
okay. Okay, yeah.
So writing, so I mean, I would have a 1 here, right?
Oh.
But sometimes it's easier just to write 1 as nothing. Or just write 1 as there. Okay. Equals, because I'm differentiating this whole expression. So I've differentiated the left-hand side. Now I want to differentiate the right-hand side. What's the derivative of y? Dy dx. Very good. That's what we're wanting to find. So now you can see how parentheses are very important because it's this expression being multiplied to both terms here. So if you drop these parentheses, a lot of times you lose out on solving for dy dx. So if I want to expand this, I have minus y squared sine of x times y squared minus 2xy sine of x times y squared times dy dx equals dy dx. Does everyone see that? I need to multiply this to each term here. So now I need to get my dy's dx on one side. It doesn't matter what side I put it on, the left-hand side or the right-hand side. So does everyone understand that next step? I'm just adding this whole term to both sides. So when I add it to this side, it goes away, and I need to represent it right here. The reason why I had to move this whole term over here is because it has a dy dx. So I can factor out a dy dx and then divide through on what's left and solve for dy dx. So I'll go ahead and write out these steps. So if I have minus y squared sine of x times y squared divided by 1 plus 2xy sine of x times y squared equals dy dx. Then I've gotten my relationship for my dy dx using implicit differentiation. So it's a function of x and y, but that's okay. I can deal with that. So, number 20. So find the slope. Huh?
That's as simplified as it gets.
That's as simplified as it gets, yeah. You can't cancel anything. So number 20 says find the slope of the tangent line to the curve at the given points. So automatically you can tell this is not a function, right? Because if I put in 10, I either get out 3 or minus 3. The relationship would be y squared minus x plus 1 equals 0. I could solve for y, and I would get two functions, right? I would get positive square root of x minus 1 or negative square root of x minus 1. But I could also do an implicit differentiation. For the derivative, if I want to plug in this point, x is going to be 10, y is going to be 3. This point, x is going to be 10, y is going to be minus 3. So let's go through the last minute. We get 2y times dy dx minus 1 plus 0 equals 0. Right? So if I solve for dy dx, I get 1 over 2y, right? So if I look at the point x equals 10, y equals 3, I get 1/6. But if I look at the point x equals 10, y equals minus 3, I get minus 1/6. So you see the equation to the slope of the tangent line at the given points. Here I have a slope of a 6, and I'm looking at the point 10, 3. Here I have a slope of minus a 6, and I'm looking at the point 10, minus 3. All right, we will finish up just a little bit more on 3.1, possibly tomorrow. If not, I'll keep you posted. Sorry for the green and purple background. Hopefully they'll get this fixed.